In this video, we are going to discuss the existence and uniqueness of some ordinary differential equations by using the contraction mapping theorem, which I recall states that if we have a contraction in a complete metric space, then there exists a unique fixed point. So let's consider the following ordinary differential equation of first order. We have a u dot that represented the derivative of u with respect to a variable, let's say t, we can call this variable time, which is a function of t and u of t. And let's assume we also know the value of u at a specific value of t, let's say t sub 0, and let's call this u sub 0. So this is called initial value problem. Now we are going to consider a function f that takes value in R cross Rn, because t is a real variable and ut takes value in Rn, and is gonna give us value in Rn. We want this function to be Lipschitz in a suitable domain, and then u is gonna be a continuously differentiable function. So f we want to be continuous. U continuously differentiable that takes value in R and is gonna give us output in Rn. The same initial value problem can be written in form of an integral equation. So we're gonna rewrite this as u of t. So the form I'm about to write is equivalent to the initial value problem we just wrote, as a u sub 0 plus the integral from t0 to t of f t ut dt. Okay, so why these two forms are equivalent? Well, if I take the derivative of u on the left-hand side with respect to time, well, the derivative of u sub 0 is equal to 0. And by the fundamental theorem, actually, to be more precise, it's not wrong to write t, but this can be a variable like, let's say, s, also u of s ds. Okay, so to not confuse with the variable t of the that we have in the integration. So if I take the derivative of u with respect to time, then the derivative of u sub 0 becomes 0. And from the fundamental theorem of calculus, what we get here on the right-hand side is f of t, u of t. And then if I look at the initial value as t is equal to t sub 0, so I'm going to plug in t sub 0 here, this integral becomes equal to 0, so we are left with u sub 0. So as you can see, these two forms are equivalent. Now we can see this, so our goal is to find the solution u of t, and we can see this in terms of a fixed point problem, in which we have a t of u of t, which is equal to u of t. So we can think of this u as our input, and this u on the left-hand side as our output. Okay, so this is our input, this is our output. So we can see this as a fixed point problem. T of u dt equal to u dt. Okay, so at this point, we want to find condition of t such that t represents a contraction. So we want to practically show that under certain condition for the function f that needs to be Lipschitz continuous on a suitable domain, we can show that t is a contraction. And since we are in a metric space, which is complete, because it's the metric space of continuous function on a suitable interval, then so in a complete metric space, we have a unique fixed point, which is the solution of the ordinary differential equation. So here we are working on a space of continuous function I, where I is an interval that we're gonna specify just in one moment. Okay, so the function u, so takes value in this interval I, and then what we're going to obtain is a continuous function I. Okay, so T is this map, okay, that takes a continuous function that is specified in the interval I and is gonna spit out a continuous function in this interval I. We're gonna consider the infinite norm. So the space Ci, where I is a closed interval with the infinite norm, is a space which is complete. Okay, so let's talk about this definition now. So suppose we have a function f that instead to be defined from R to Rn is defined from I to Rn. It's going to give us value in Rn, where I is an interval of the real number R. And we say that f tu is Lipschitz continuous of u uniformly on T if there exists a constant C greater than 0 such that, so if I take the norm of f tu minus f of t d, and this quantity is going to be less than or equal to C norm of u minus norm of v. So here we're going to consider the infinite norm, okay? But I'm not going to write every time infinite norm, so anytime I write norm is the sup norm, okay? So this means that f is Lipschitz continuous, more precisely is going to be globally Lipschitz continuous, okay? All right, because u is defining all Rn, okay? All right, so based on this one now, based on this definition, we can state and prove the theorem of existence and uniqueness. Okay, so what we're gonna do is, so let's take this theorem. So the theorem says, suppose that we have this function f that goes from I cross Rn to Rn, where I is an interval of R, and let's assume, well, let's recall first that we are working this initial value problem u dot equal f of tu, and then u at time t 0 is equal to u sub 0. That's called initial value problem. All right, so we want f to be a continuous function, well, Lipschitz function, just in 1 second, I'm going to state it more precisely. So a function from I cross Rn to Rn. I is a subinterval, is an interval of R, so it's a subset of R, and this point t0, t sub 0, we want to be in the interior of I, so let's say I with this superscript 0, this means the interior of I, and if f is Lipschitz continuous, okay, so Lipschitz continuous of u uniformly in T, in this interval I cross Rn, and if f is continuous, so we also want to be continuous on Tu, okay, um, continuous of Tu, precise to say of Tu, then there exists a unique unique solution, which is the fixed point of the contraction, so a unique solution of the initial value problem. Okay, so in order to prove this, first thing we need to make sure is that T is a contraction, okay? So we are going to consider our interval I equal to T sub 0 and then T sub 0 plus delta, where delta is a value that we are going to specify, okay? Okay, so we know that f is Lipschitz continuous. So now let's consider two functions, u and b, that goes from this interval I and give us value in Rn. And based on the contraction t, we have that t, well, we want to show that t is a contraction, so we're going to consider, we're going to estimate the value t of u minus t of b. So what's this equal to? Well, this is equal to, so here we have the infinite norm, so by definition is the sup for t that goes from t0 to t0 plus delta of the integral from t0 to t of f of, so we have a s, let's use a variable s here, so s u of s minus f of s v of s, then we have ds, and the initial value here, since we are taking this difference, tu minus tv, the u sub 0, which is the same, is going to cancel out. So that's why it doesn't appear in this integral equation. And here we have the norm of this function. Okay, so practically we have tu minus tv. Alright, so at this point, what we can do is rewrite this as less than or equal to what? Well, the sup, so the norm of the integral is less than or equal to the integral of the norm. So we can write sup of t between t0 and t0 plus delta of the integral from t0 to t of the infinite norm of f of s us minus f of s vs and then ds. Okay, but this is then equal to what? Well, this is, since this is the infinite norm, okay, that's the infinite norm, that's doesn't depend anymore on the variable s that goes from t0 to t, so we can take this outside the integral, okay, and then the sup from t0 to t of ds is a t0 plus delta, so we can write this as norm of f of s us minus f of s bs, so here we have the sup norm, times t0 plus, well, if we go from t0 to t0 plus delta, then the integral is going to be just delta. Now we're going to use the fact that this is Lipschitz continuous, of u uniformly in T. So this quantity is going to be less than or equal to C times delta, and then we have u minus b. Okay, we have this the sup of u of s minus v of s. Okay. All right, so in this point, what we have is that in order to have a contraction, we want this quantity, which is a constant, to be less than 1. So we want C times delta to be less than 1. Based on this one, we can choose the value of delta to be less than 1 over C. So our interval, I, which goes from T0 plus, well, T0 to T0 plus delta, is going to become T0 plus T0 plus delta, where this delta needs to be a quantity which is less than 1 over C. If this is true, then we have a contraction, and T represents a contraction that goes from the space C of I to C of I, which is complete with the infinite norm. So we have a complete metric space, we have a contraction, and by the contraction mapping theorem, so by the contraction mapping theorem, there exists a unique fixed point, let's say U star, which is the solution of our ordinary differential equation, since the Tu star is going to be equal to U star. Okay, and this satisfies the initial value problem. Okay, so at this point, let's take a look at some examples of such ordinary differential equations. Okay, so in this first example, we're going to consider a linear ordinary differential equations with continuous coefficient. So we're going to have an equation in the form u dot of t equal to a of t, u of t plus b of t, and then we have the initial value u of 0 equal to u sub 0, where a is practically a matrix that takes value in R and give us an output in Rn cross n, and then we have u of t is a vector, okay, that pick up a value in R, so you pick up a value in R and give us value in Rn, okay, and then b of t, so b takes value in R and give us value in Rn. So when we multiply this metric A by U, we get a vector, and we can add that with this other vector. And U sub 0 is equal to U0. So that's our initial value problem. Okay. Now, we can show that for any bounded interval I, containing R, there exists a constant C greater than 0, such that the norm of A, so we can consider here also the two norm. So norm of A multiplied by U is less than or equal to this constant C times the norm of U. Okay. Now, in order to show this, well, let's say that the elements of matrix A are I, J. So this product, if I take AU square, then this is equal to the sum I and the sum j, so I goes from 1 to n, j goes from 1 to n of I e j square uj square, And at this point, by the Cauchy-Schwarz inequality, this quantity is going to be less than or equal to sum I, and then we have sum j of ij square times sum j of uj square. And now this is equal to sum j, well, this is sum I actually, even though I and j goes from 1 to n because it's a square metric. So here I have a sum I, sum j of ij square, so I can group this, times sum j of uj square. And this quantity represents the norm, the 2 norm of A square, and this represents the 2 norm of U square, okay? And therefore, this is our constant C, which is the square, which proves this statement. Okay, so now that we prove this statement, what we have, so this right-hand side of the linear differential equation represent our f of t, u of t, and if I take the difference between a of t u minus a of t v for two continuous differentiable function u and v from R to Rn, then based on this inequality, this is going to be less than or equal to a constant c u minus v, which implies that this function f is Lipschitz continuous in u uniformly in t, and therefore what we have is that the conditions of the theorem that we just proved, all the hypotheses are going to be true, and therefore what we have is a unique solution in our interval, okay, in our interval I. By the way, the interval I is an interval, if you remember, we said it goes from t0 to t0 plus delta, where this delta was less than 1 over c. Now, we can repeat this process, of course, for, an infinite amount of intervals that, they're all going to overlap, and therefore we can prove this same uniqueness, this uniqueness of solution in the entire real line. So more than a global solution, well, more than a local solution, we have a global solution because we can prove this for the entire real line. Okay, so one last example is the one of the ordinary differential equation, which is non-linear. Okay, so here we have, so let's write down this example. Okay, so we have this a nonlinear ordinary differential equation. So u dot is equal to the square root of a of t plus u of t, both of these square. And then we have u sub 0, which is equal to u, u of 0 at time t equals 0 is equal to u sub 0, where a that goes from r to r is going to be a continuous function. So here, this right-hand side represented of t u of t. And we want to prove that this is a Lipschitz continuous function of u uniformly of t. So to prove that, let's estimate the difference between f of t u minus f of t v for two functions u and v. So what we have is that this quantity is equal to the square root of a squared plus u squared minus the square root of a squared plus v squared. Okay, and now what we can do is divide the square root of a squared plus u squared plus the square root of a squared plus v squared, and then we divide by the square root of a squared plus u squared plus square root of a squared plus v squared. Okay, so here we have this product. So if we multiply this, what we're gonna have by the difference of square formula, this is equal to the absolute value of a squared plus u squared minus a squared plus b squared, so a square, the square cancel out, and then divide by the square root of this quantity that are both positive. So this is equal to u minus v times u plus v, and then divide by the square root of a squared plus u squared plus the square root of a squared plus v squared. Now, notice that this quantity is going to be also, well, less than 1. And therefore, what we have, we can call this, a constant c. So what we have is that f of tu minus f of tv is going to be less than or equal to this constant c times u minus v, which implies that this f is Lipschitz continuous. And again, the condition of the theorem that our hypotheses are satisfied. This will imply that we have a unique solution of the ordinary differential equation.